Hi, Marc Hendrix back with AIM Geoanalytics for week 2 of our Phosphoria webinar. This week, we're going to have a closer look at the petroleum system of the Phosphoria. Recall that we're in a 5-week webinar. We already had week 1, introduction. We're now on the Phosphoria Petroleum Reservoir. We'll have 2 more webinars, weeks 3 and 4, looking at the lithophases, and then we'll sum it up in week 5. We're looking at a core here of the Pennsylvanian Ten-Sleep Formation from eastern Wyoming in the Bighorn Basin, and this particular core is full of oil that has been typed to the Phosphoria as its source, as I'll describe a little bit later on today. All right, well, let's go ahead and get started. So week 2, Phosphoria Petroleum System. You might remember this chronostratigraphic chart from week 1. This is looking at the entirety of the Phosphoria Basin from the southern portion to through the middle to the northern part, and we're looking here at not only reservoirs within the Ten-Sleep and the Phosphoria that are charged with oil and gas, but we're also looking at the overall stratigraphic complexity of this formation. So it includes a number of different members: the Grandeur, the Mead Peak, the Franson, the retort, and so forth. Remember, the Mead Peak and the retort are of particular interest to us in this webinar because these are the organic-rich phosphatic mudstones for which the Phosphoria is famous and for which its oil, for the most part, was sourced. Okay, well, let's look at both of those two mud rocks in sequence. Starting with the older of the two, this is the Mead Peak phosphatic member of the Phosphoria Formation, shown here by way of paleogeographic reconstruction. Now, this is work that was published earlier by Edwin Mon of the U.S. Geological Survey, and what he and his colleagues are showing are the distributions, the modern day distributions of the organic rich mud rock associated with the Mead Peak. And you can see that its equivalents to the east and to the north include carbonate, limestones and dolomites, and then sandstone. And you also see on this map thicknesses. This is an isopac map. The thicknesses are contoured in pink. And then also isopleths. Now, these contours show the percentage of TOC, total organic carbon, within the Mead Peak member. So you see there's a relatively thin, actually less than 1 meter thick, occurrence of Mead Peak phosphatic mudstone in southwestern Montana, and it has a relatively high TOC, but it's, again, very thin. Here in southeastern Idaho and adjacent parts of Wyoming and northeastern Utah, the Mead Peak actually becomes quite thick. It's up to over 60 meters thick, and there it has relatively high TOCs, as well as high as in excess of 8%. So this is the sort of depositional basin that's associated with the Mead Peak, the older of the two phosphatic shell members of the Phosphoria. Here's what the Mead Peak looks like in thin section. This is just a scanned thin section of the Mead Peak, a little close-up plain polarized light image of that formation of that facies. You can see a scale bar here at 100 microns, and then some simple XRD mineralogy that we acquired at AIM Geoanalytics. This particular sample is an example of massive organic rich silty dolomudstone. So there is a little bit of dolomite in the sample. Most of the sample, however, is quartzose and feldspathic, and both of those two minerals, as you can see here in this thin section, are in the form of detrital silt. So these silt grains, angular grains of detrital silt, actually are very common in the Mead Peak, and it may be more properly referred to as a siltstone in some places, although throughout the literature it's referred to as a shale. So here's another example of what the Mead Peak looks like in its depot center. Now, this particular sample has about a 5.5% TOC and is in fact mostly a carbonate in terms of its inorganic mineralogy. So about 82% dolomite here. You also see some calcite and a few percent of the siliciclastics. All right. Let's move to the retort member. Now, this is the younger of the two organic-rich mudstones within the Phosphoria. And for the most part, the retort is best developed in southwestern Montana. You can see here, again, this is work from Edwin Mon and the USGS 1975, that the thicknesses are thickest, the thicknesses are greatest here in southwestern Montana. So the Mead Peak here, excuse me, the retort member gets up to about 8 meters thick in southwestern Montana, and it only is as thick as about 2 meters here in southeastern Idaho and adjacent parts of Wyoming and so forth. In terms of the isopleths that are shown by this map, percentage of TOC, these are really exceptionally organic rich rocks, not only down here in southeastern Idaho where you have a thin occurrence of retort, but in southwestern Montana where multiple samples have come in with measurements in excess of 30 weight percent TOC here. Most samples are a little less than that, but very high nonetheless. All right, let's look at a few samples of retort. These are from southwestern Montana, and you can see here that you've got not only quite a bit of detrital silt by way of these small grains here, but also some bigger grains. These larger opaque grains are phosphatic peloids. You see in terms of its mineralogy, again, we're seeing a lot of quartz silt. So this brings up the question, where did all those quartz silt come from that we're seeing in both the Mead Peak and the retort? And the answer is it's most likely to be aeolian, driven off of the Pangaean continent by those trade winds that we talked about in the last webinar, those northeasterly trade winds coming from the northeast off the continent, blowing oblique the shoreline and delivering a lot of silt from that desert environment to the offshore region into the Phosphoria Basin. Here's one more example of the retort. This also from southwestern Montana. Here we have a very high TOC, on nearly 20% we measured, and you can see here that you've got, again, a lot of quartzo silt as well as quite a bit of clay, in this case illite. So bottom line here, in the case of the retort, we have exceptionally high TOCs, also high TOC in the Mead Peak, which is more widespread, but perhaps a little bit less organic rich. And in both of these members, we see a lot of aeolian silt. Okay, let's look a little bit more geochemistry from both of these two members within the Phosphoria. Looking at the two members in terms of their stratigraphic relations one to the other, they actually occur in two different stratigraphic sequences. That is to say, they're both a part of an individual unconformity-bound package of rock that is genetically related and is separated by sequence boundaries. So looking here at some data from Hyatt and Budd 2003, they collected a number of samples across the Phosphoria Basin in western Wyoming and in southeastern Utah. They didn't get up into southwestern Montana. And so these are all of their data looking at TOC versus total sulfur and weight percent. And you can see that they have really two clusters of data, those that are interpreted to represent anoxic depositional conditions, shown here by the brown dots, and those that are shown interpreted to represent euxinic conditions, those shown by the blue squares here. In case you're not aware of what euxinia is, it's kind of an unusual word. It refers to very chemically reducing conditions, very low EH conditions, in which hydrogen sulfide is able to dissociate straight from liquid phase, come out of solution, that is, into a gaseous phase. So you have exsolution, excuse me, not dissociation, exsolution of hydrogen sulfide directly in the water column. And this can lead to the deposition of framboidal pyrite as that hydrogen sulfide complexes with any available iron. Okay, now Hyatt and Budd also looked at separated their samples just from the Mead Peak in this plot here, and you can see that most of the Mead Peak samples appear to plot in areas that are characterized by depositional anoxia as well as dysoxia. Only a few plot into the euxinic field here. So what we can conclude from these two plots here is that most of the Mead Peak appears to have been deposited in an anoxic environment. Most of the rest of the phosphoria, including the retort, appears to have been deposited under a euxinic environment. So also anoxic, but it has sufficient hydrogen sulfide to exsolve out of solution. Here are some other relevant data. These are biomarker data from Dahl et al. 1993, looking at rocks from the lower sequence, including the Mead Peak and at the overlying chert called the Rex chert, and the upper sequence, sequence 2, which includes the retort as well as its overlying chert called the Tosi chert. And so what Dahl et al. Are showing here are 3 biomarker indices that basically indicate that there is a difference between these 2 depositional sequences. This first index, the gammaserine index, is a salinity indicator, suggesting that the upper sequence was more saline than the lower sequence. This middle index, the homohopane index, is an anoxia indicator, suggesting that conditions were more anoxic during the upper sequence, a little less anoxic perhaps during the lower sequence. And then finally, this third index is a ratio that is intended, or that is interpreted to decrease with anoxia. So again, the upper sequence having a decreased index here in this case suggests the higher levels of anoxia. So we have different paleoceanographic water chemistries that appear to be part of this this entire phosphoria complex, but more specifically, the 2 major organic rich mud rocks appear to have had relatively different bottom water chemistries. All right, looking at some more geochemistry of samples from the phosphoria, the panel on the left is from Jeremy Dahl and others in 1993, and they're showing here a series of gas chromatograms that were derived from rock extracts both within the retort member of the phosphoria as well as in the Mead Peak member of the phosphoria. They've organized these data into samples that were of low thermal maturity, of mature thermal maturity, and high thermal maturity. And they included, again, both the retort and the Mead Peak in this analysis. What these data show are in all 3 thermal states, the 2 organic rich members of the phosphoria both generate significant volumes of hydrocarbons, and that that both are reflective of very good source rock generative potential. On the right panel, we're looking at 3 separate time temperature diagrams of samples of phosphoria from 3 separate localities. The upper diagram is a sample of retort formation, retort member from the Grovant Slide area in Wyoming. Middle panel here, a sample of the Mead Peak from the Idaho Thrust Belt that in this particular case has not been too deeply buried. And then the lower panel showing a similar Mead Peak sample, but this one more deeply buried. You can see the measured vitrinite reflectance values from each of these 3 samples, and also the time temperature pathway that each has experienced, both during the subsidence phase that led to the thermal maturity that each of these samples exhibits, as well as the uplift phase, which brought each of these 3 outcrop samples to the surface. The main point being here that the phosphoria and its 2 organic rich mudstones are present in a fairly in a very locally tectonically complicated, structurally complicated setting. So the specific structural configuration of each portion of the Phosphoria Basin, whether it's in the fold thrust belt, in a relatively deep structural setting, in a relatively shallow structural setting, or whether it's out of the thrust belt itself, all have important ramifications as to the thermal history, and hence the ability of these 2 members to generate petroleum and gas. All right, now some GC gas chromatogram mass spectrometer data, where this is from Seifert and Muldowen in the early 80s, where they were looking at rock extracts from the Cretaceous, Maury rock extracts, versus oils that are interpreted to have been derived from the Cretaceous Maury. And they were comparing these with rock extracts and oils that were interpreted to have been sourced from the Phosphoria Formation. Those are shown here on the panel in the right. And so what they're showing then is that there are actually a good correlations between rock extracts of the Mowry and oils from the Cretaceous reservoirs within Wyoming basins that do correlate on the basis of these specific biomarkers. These are individual molecular compounds that in aggregate form a sort of a barcode that allows one to correlate a particular rock extract with the oils that are generated from that rock extract. So again, we have the shale, the rock extract on the top GCMS trace here, and then we have a series of oils in the lower 4 traces. Looking at the Phosphoria, we see again a Phosphoria rock extract from southwestern Montana. This is actually from the retort, and we see here in various oils very similar looking pattern of in this case Hopanes. That's the biomarker that is being used to correlate these Phosphoria oils to its source rock. So the point of this is that throughout Wyoming and in much of the northern Rockies, the 2 main sources of produced petroleums are the Cretaceous Interior Seaway and its associated organic-rich mudstones, and the Phosphoria Formation. Okay, this last slide is from Jim Peterson, published in 1980, and what he's showing here are, first of all, an isopack map across much of western Wyoming. That isopack map shows everything from Permian through Cretaceous, and it's interpreted to represent essentially a proxy for sediment distribution that was laid down from Permian time forward. He's also showing here in green the places where the Permian Phosphoria was largely carbonate in terms of its depositional facies. He's showing where Permian is exposed today at the surface, and that's where most of these measured outcrops the data were collected. And then he's also showing places where he's got well control. So he's got well control with the purple dots, measured sections with the black X's. And then finally, he's showing here the inferred migration pathways for Phosphoria oil as it was expelled out of the foreland thrust belt, particularly in southeastern Wyoming, where the Mead Peak is both thick and thermally mature, and then through secondary migration, mainly through the 10 sleep, with the Dinwiddie, overlying Triassic Dinwiddie serving as a regional seal. That migration was, in fact, several hundreds of kilometers to the north and to the east, where it ended up forming a very large reservoir that subsequently was broken by the Laramide uplifts that today leave us the Bighorn Basin versus the Bighorn Mountains, the Wind River Mountains, and so forth. So this migration story is one that predates the Laramide partitioning of the Foreland Basin. And that partitioning remobilized some of these Phosphoria oils higher up into the stratigraphic column and distributed them pretty much into the configuration that we see today. Okay, well, that's it for this week's webinar. Next week, we're going to take a look at some of the lithofacies that we see in the Phosphoria as we at AIM have been able to gather from outcrop data. So this is Marc Hendrix. I'll see you then.